Okay, thank you everybody. I must say this is the first time I'm presenting this in a Hawaiian shirt, and I think I might just do that from now on. So thanks for the opportunity, Bill, for adding me to the agenda last minute. Appreciate the opportunity to talk to you guys. So I'm representing a company called Alta Devices. I'm the chief marketing officer there. And we are a solar cell technology company, but for now, and I'll talk a little bit more about this, we actually consider ourselves more of a mobile power company and not so much a traditional solar energy company. So if you think about power, obviously everyone needs power to basically drive lots of different things, right? Whether it's your car, your cell phone, or your sensor, you're always reliant on some type of energy source. The problem is if you run out of power and you're nowhere near that energy source. So this is the problem that we're really focused on, is providing power in places that you aren't near the grid or have access to some other energy source. So if your car runs out of power, if your cell phone runs dead, or if you're in the middle of nowhere, or if you happen to have a battery that ends up dying, all these needs really cry out for some other type of solution that provides energy while these things are being used. So that's kind of what I mean by mobile power. So if you look at the kind of markets that we address, all these things have one thing in common. They either move or they fly or they're carried, and they have some kind of battery internal to them. And what we do is we look for places where we can apply our solar film to the surface of these devices and provide charge while these things are actually being used throughout the day. So we have been around for quite some time. We were founded in 2008, so we're about 7.5 years old. In 2011, we set the world record for solar cell efficiency of any solar material ever made, and that's 28.8%. And we've held that record ever since. And the other thing that's unique about our technology is it's really thin and flexible. So this is a solar cell, so it's very different from what you'd think of as a solar cell. It's obviously very thin, very lightweight, very flexible. It weighs about 1 gram per watt of generation. So that's also quite special and really advantageous in a few key markets. And the other thing about this technology is it operates in very low light situations. So unlike most solar technologies that need sunlight, we can actually work from indoor light, which is really good for a lot of the sensor applications that I was even hearing about earlier, right? Motion sensors, temperature sensors, all those kinds of things could benefit from an additional power source to keep those batteries lasting longer, or possibly even eliminate batteries altogether and those kinds of things. So if you guys aren't familiar with PV technologies, there are a myriad of ways to do solar. Everything from, organics and amorphous silicon, all the way up through, what we do, which is gallium arsenide. So as you kind of move left to right along this chart of efficiencies, you see one thing that happens is you go from a flexible form factor to a rigid form factor. So traditionally, to get efficiency, you needed to go to a wafer-based rigid kind of solar cell. And so that's what really kind of makes us different, is we chose to use gallium arsenide, which we knew was going to be a great solar cell. It's been used in the space program forever. But we needed to make it cheap, and we needed to make it thin, and we needed to make it flexible. And that's really what Alta Devices was founded to do back in 2008. So a couple minutes on how we make what you see here, because it is quite different and quite unique. So we start with, as I mentioned, gallium arsenide. So everything starts out in wafer form. So we literally purchase off-the-shelf gallium arsenide wafers. They come in 4-inch square form factor, which is what you get out of a 6-inch round. And that's our sort of seed or our starting point. What we do then is we take that wafer, which is quite thick, it's about 650 microns thick, we put it into a reactor, and using a process called MOCVD, which is metal organic chemical vapor deposition, we start growing, basically depositing layers on top of that wafer. And as we do that, we keep the same crystal structure throughout. But because it's gallium arsenide, which is a 3-5 material, we can mix and match the gallium or the arsenide with other materials and still keep a nice crystal structure. So that's important because that first layer we put down is actually aluminum arsenide. So it's not gallium arsenide at all, but it looks like gallium arsenide from a molecular level. It's got the same crystal structure. Then we turn off the aluminum, turn on gallium, and lay down a nice layer of gallium arsenide. Once that's done, we deposit a layer of copper, which becomes the back metal, and then we cover all that with a plastic laminate, basically a layer of PET. And then once we have that whole sandwich of all those different layers done, we take that whole thing and we put it into a vat of hydrofluoric acid. So that step is basically where the magic happens. The hydrofluoric acid reacts to the aluminum arsenide differently from everything else, and it essentially etches away that yellow layer that you see there. And so that's the point where whatever we grew above it becomes separated from whatever was below it. And the wafer that we started with just goes back to the beginning again, and whatever we grew on top becomes this. This becomes that solar cell. So that's how we control how much gallium arsenide we actually consume in the solar cell itself. It also gives us our thin and lightweight and flexible form factor. So at that point in the process, what you see is this. This is a 4-inch tile that was removed from a wafer. It has gallium arsenide on one side and copper on the back side. This also has a plastic lamination around it just to protect it. But if you guys are interested, you can always come up afterwards and take a look at this. So then the next step is you flip it over, and then you basically finish it by putting front metal on the actual gallium arsenide, and that's what turns it into a solar cell. So we put front metal on it, we cut it up into individual cells, then it looks something like this. We actually make 10 cells out of that 4-inch square tile. And then once we have individual cells, so this then gets laser separated and then stacked into cassettes, we can then reassemble these cells into larger sheets. So you can imagine basically any size you wish. You can turn it into a sheet that's got, some kind of flex to it. There are lighter or thicker variations of this lamination material, whether it's going on an automotive roof or a UAV wing. It becomes a very thin and lightweight solar array, basically. So a couple of case studies in terms of the kinds of markets that we're going after. Certainly one is UAV. I mentioned it just a second ago. This is a really important market for us because it enables such a huge value add in the aircraft itself. So I'll show you a case study that we've been working with a customer called AeroVironment. I think we need to turn the volume up.
What we're doing is a solar flight. We've got a solar panel on the main wing of the air vehicle, and we're going to see how long we can fly today. So this project's been going on, I think, for roughly about a year. So today, being it's summer, we're expecting probably somewhere between 8 hours and possibly up to 9 hours and 45 minutes. Had a nice, long, successful flight. 9 hours, 11 minutes, and 45 seconds.
So that Puma would normally fly for about 2 or 3 hours.
Really well. It's very smooth, and we're pretty happy with the outcome.
So you can imagine if you're out in the middle of nowhere and you have to keep retrieving these UAVs and recharging the batteries, having an all-day solution is quite valuable. So there's a whole bunch of markets beyond the military that will be able to take advantage of this technology. There's a whole civil UAV market developing. There's a whole high altitude UAV market for providing internet services, people like Facebook and Google are talking about flying these high altitude UAV platforms, which will obviously need lots of solar power as well. So that's a key area for us, but it's only one of many different end markets. Another one is soldier power. So, one of the areas of interest for us is the ability to provide a soldier a solar blanket or a solar mat that they can carry with them. And if they're stuck out in the middle of nowhere, they always have the ability to recharge their critical electronics. And these things have been out in the market for quite some time. Here's an example of 3 different versions or 3 different technologies that are out in the marketplace. Ours is that small little mat that you see there, and then the 2 behind it are more traditional ones that are available using either amorphous silicon or SIGS PV technology. They all produce the same amount of power, so you can see the drastic size difference between our version and what's out there today. So you can carry either more power with you for the same weight, or you can carry less weight and get the same amount of power, depending on which one's more important to you. And then on the indoor or sensor market, we also produce quite a bit of power from ambient light. So here, the real focus is to provide, microwatts of energy, and it doesn't sound like a lot, but it's quite a bit more than any other PV technology that's out there, and it's enough to basically power a smoke detector or a motion detector or some other kind of wireless radio sensor indefinitely. So that's another key application for us. And then finally, there's the whole consumer electronics market. So for cell phones and wearables, by putting solar into the product itself, we can make those batteries last longer as well. So a couple example data points, 1 minute of sunshine gives you, 10 minutes of standby time, or 10 minutes of sunshine gives you 10 minutes of talk time. So if you needed to make a call, all you got to do is just get a little bit of sun, and then your phone can turn back on again. And in the wearable space, it's even more significant because these things tend to be much lower power. So you go for a 30-minute run, and you get hours, multiple hours of extra battery life on like a Fitbit or some other kind of smartwatch device. So those are kind of the best examples of where you'll see our technology first applied. And then we heard a lot about the sort of energy market in general from the other speakers. That's certainly on our roadmap and one of our targets. We're trying to just take one step at a time. So right now we have a small factory that we're building in Sunnyvale. We're currently operational on that. We're producing solar cells today. We are generally sold out for 2015, selling into a lot of the markets that you saw here. And we're scaling hard. So in 2016, we'll have around 1 megawatt of capacity. In 2017, we'll have about 3 megawatts of capacity. And then we're building even larger factories beyond that. And as you can imagine, our costs come down as our scale goes up. So our models definitely show a trajectory to get to that magic, dollar per watt number down the road. In the meantime, we're looking for opportunities where, there's a much higher value add for the technology in places that other things just can't solve those problems. So, yeah, I guess I'll have to say it. Our future seems to be very bright as a PV company. I hate to use that pun, but it seems appropriate. And that's all I had. So I'd love to hear some questions or comments, or anybody has anything to ask.
What's the cost comparison? You talked about the output comparison, but
Yep.
Take those 2 other solar blankets that you had before. How much does yours cost compared to theirs?
Yeah, so we're, it's. So I don't know if you guys heard the question. What's the cost comparison to other solutions out there? It's changing over time. Today, we're about 10x more expensive. It's just because we're just getting started with our production. We'll be, equivalent to those solutions in about 2 years. And then we'll be on our way to being more cost competitive with even sort of traditional silicon PV. That's probably 5 years out. kind of give you an idea. Okay.
Thank you so much.